Welcome to the lecture on storage devices. So we will talk about a bunch of storage devices, primarily flash drives and hard disks. We'll also talk of NVMs a little bit, not much. So the main idea with flash drives is that they are ubiquitous. They are solid state drives in the sense they are built on top of transistor technology, and if you turn off the power, the data is still retained. So a flash drive is something we have all seen. This is how it looks, right? We all use it. How does it work? Well, so to store one bit, all that you need is one transistor. So as you can see over here, we have a source, we have a drain, and then we have a channel. So this is what a regular NMOS transistor would look like, and we would have a silicon dioxide layer which is nothing but the dielectric, and we would have a control gate which is made of polysilicon, a gate which is made of polysilicon. In this case, what you have is you have one of these polysilicon layers sandwiched between the real gate and one more dielectric layer. So this part is extra. So this part is called the controlling gate or the control gate, and this part is called the floating gate. The main idea with the floating gate is basically that it lies between the gate that actually controls the operation of the transistor and the channel, right? So it's an extra gate in between, which is not there in a normal transistor. So now you will ask me, why is it required? Give me 2 minutes. Also, we will have this symbol over here to represent one of these transistors with a floating gate, where you can see the floating gate is over here. So we have introduced an additional gate. What can we do? We can trap electrons in it. So what we can do is that we can have a positive charge and then we can trap. Okay, so then if we have a positive charge, it will pull electrons from the channel, and some of them can get trapped in the floating gate, and that would change the threshold voltage of the transistor. So that sounds like a great idea, because it is a great idea, and all the flash devices are on the basis of it, right? So this is the basic physics. So what we do is that now we have two states for the device. One is that the charge is trapped, one is that the charge is not trapped. So charge is not trapped is the default state, but let's say I apply a very positive voltage here, and then electrons go up, 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 and some of them get trapped over here. That is a programmed state, which even if I take off the power, right, take it off the supply, the electrons will still remain. And so that is a programmed state where the charge is trapped. So I would say that is a logical 0 for me, and this is a logical 1 for me. So this sounds simple enough. So for logical 0, right, this is when does a logical 0 happen? It happens when charge is trapped. Where is charge trapped? Charge is trapped in the floating gate. So the threshold voltage when the charge is trapped is Vt plus, which is high, which is higher than normal, and the normal threshold voltage is 1, which is kind of the unprogrammed state, right? And this is the regular threshold voltage, and the other one is kind of the enhanced, it's kind of the enhanced threshold voltage. All right. So we have two kinds of threshold voltages now, Vt and Vt plus. The moment charge is trapped, it's in this Vt plus zone, which is a logical 0 for us. So given that electrons are negatively charged, for creating any kind of a conducting channel, you will have to apply a higher threshold voltage, which is exactly why when charge is trapped, the threshold voltage increases, which means that Vt is less than Vt plus. So how do we figure out? So how do we read the value of a cell and figure out if it's a logical 0 or a logical 1? That's very simple. For the control gate, we set the threshold voltage, which is between Vt and Vt plus. If the transistor is conducting, it's a logical 1. If the transistor is not conducting, it's a logical 0, as simple as that, right? And we would just want to ensure that the difference between Vt and Vt plus is more than the noise margin. All right. So this is quite simple physics. Still, if you are having issues understanding it, you look at the, look at any basic text in electronics and the answer will be found there with regards to what is the threshold voltage. The rest, once you understand that, the rest is somewhat easier. Writing to a floating gate transistor, again that's not very hard. Writing a 0, which is programming, basically means what? You want to apply a very strong voltage at the control gate such that all the electrons rush towards it. The moment they rush towards it, some of them would get trapped in the floating gate, would remain there, right? So the resulting electric field will of course pull electrons up, but finally, the electric field at one point will also kind of oppose electrons, so it will have a repulsive force where it will repel electrons downwards, but some equilibrium will be set up. But the end result, or the long and short of the entire discussion, is that in the floating gate we will have electrons which are stuck. Similarly, if I want to erase it, if I want to erase it means writing a 1, which means taking it back to its default state. Then what I do is I do the reverse. I apply a strong negative potential such that whatever is there at the floating gate, all the electrons, they are kind of pushed back into the channel and they go back to the channel. So then the cell becomes unprogrammed, deprogrammed, right? Whatever you may call, I would say erased. So in general, 0 I would say programmed, 1 I would say erased. There are two configurations of flash cells. So one thing is clear, that as opposed to a regular transistor, we are applying very high voltage over here. So we are applying a high positive potential and a high negative potential that has its own power grid issues. So basically it is not very easy to actually build all of that infrastructure for a single cell. We would like to have a bunch of cells and kind of access them together such that we can share this high positive potential, high negative potential infrastructure. This means that we need to kind of pack our cells, increase our density and access them, as we will see, in a more or less special manner. But don't care that much about latency, because these are not memory devices, these are storage devices. Insofar as storage devices are concerned, they just need to be able to hold on to the data. They need not be that fast, because the aim is never to use them in an online mode, like where from the caches data kind of flows over there. That's not the aim. So the aim with NOR flash over here, which is the older technology, it's not used, but this is something still worth knowing. NOR flash, it's not used though, is that we have two of these transistors, one after the other, and one end is connected to the ground and the other end is connected to a bit line. So we will see how it is accessed in the next slide. In comparison, in NAND flash, what we do is we have a bunch of these transistors connected in series, one after the other, and to enable them we just put a 1 over here, a logical 1. The logical 1 kind of closes this switch, because a transistor is nothing but a switch that connects the bit line to this series of transistors, and the ground select, if you make it 1, it will connect this to the ground line. All right. So clearly we have a high density here, a very high density. So now let us look at NOR flash. So NOR flash, this is the basic circuit, this is the ground. So it saves only 2 bits. Every cell stores only 2 bits. Only one of the transistors is enabled, and the voltage there is set between Vt and Vt plus, right? So basically, let's say you decide to enable this transistor, you set its threshold voltage between you set it here. The moment you set it between Vt and Vt plus, so clearly if it is logical 0, so let's say if it's logic 0, so what will happen is it is not going to conduct. So it's not going to conduct, and the bit line is pre-charged to logic 1, in the sense that you already put in a potential of a logic 1 over here, you pre-charge it, because there is no path to ground, right? If this is logic 0, at the end, if it's logic 0, the output will be 1, and if let's say the cell stores logic 1, or the transistor in consideration stores logic 1, in this case it would conduct, so there will be a straight path to ground. and the bit line will get discharged via this path. So which means that you will actually read 0 here. So what you read over here at the end is nothing but is basically nothing but the reverse of the value that is actually stored. So this is similar to a DRAM cell. In terms of usage, it is similar to a DRAM cell. The reason being that a DRAM cell would be something like this, and basically a flash cell in this case would be slightly different, in the sense one transistor would be enabled, and that enabling basically means setting the threshold voltage between Vt and Vt plus, and after that what you do, once you do that, is that you precharge the bit line and then you connect the transistor to the bit line and see what it does with it. If it discharges it, it's storing a logic 1. If it is not discharging it, stores a logic 0. So whatever you read at the end, you just flip it once using an inverter and your job is done. In fact, the final output over here, you just use a regular inverter and you flip it and your job is done. This is easy, simple, impractical and inefficient, hence it is not used. What is used is a NAND flash. And NAND flash, how does it work? Well, you enable the bit line select. So you push this switch, you push this switch, and a bunch of these transistors are connected in series. So you set the voltage on the bit line select and ground select both to 1, you connect them, and let's say we want to read the value that is stored in transistor WL5. So in WL5 if you want to read, then what you do is you set the voltage between Vt and Vt plus, which is nothing but enabling them. For the rest of them, you create a straight conducting path to ground and the bit line. So for the rest of them, you set the threshold voltage or the gate control voltage to Vt plus, which means regardless of the value that they store, 0 or 1, they act like a wire in the sense that they are conducting. It's only this one that we have enabled and this one that we want to look at separately. So in this case, what will happen is the same thing. If it is programmed, it will have a logical 0. If it's a logical 0, it's not going to conduct. So the bit line will maintain its precharge voltage of 1. If it is not programmed, it has a logical 1, then it will conduct, and then the bit line will be set to a 0 value. So this has a 40 to 60% higher density than NOR flash, hence NAND flash is used. We could also have, or maybe as an option have, multi-level flash, where we can store multiple bits per cell. Not necessary to store one bit, but let's say if we can have 4 different levels, in the sense, let's say that in this case we have several threshold values. So then we can see that we can have several kinds of ways of enabling a cell by putting it in different zones and seeing whether it is conducting or not, right? Or we can see even if it is conducting, right? So conducting is not a 0-1 thing. We can treat a transistor as an analog circuit and we can see how much of current is it conducting. If let's say we put the threshold voltage there and it's sort of there in its linear zone, right? How much of current it is conducting, right? So we'll have to look more at the physics of the cell. But the idea is that we can store multiple bits per cell, which would be 1 to 4 bits per cell. In general, if we want to store n bits, we will need 2 to the power n distinct charging levels. So most of the flash devices that you see these days are actually multi-level flash. That one device actually stores multiple bits. Idea is the same. Idea remains the same, that the charge that is kind of stuck in the floating gate determines the threshold voltage, and you use that to accurately sense based on the current flow what is the voltage, and the logic level that this is representing. Higher storage density, no doubt. Of course, this has a lower endurance, a lower shelf life. That is always a problem with these flash devices, that the shelf life is low. Why, we will see in the next 3 slides. And of course, we need more ECC and error correcting codes. Alright, so I promised you I'll talk to you a little bit about the redundancy aspect, and the redundancy aspect is like this, that flash devices are not memory devices. Never make that mistake of thinking that a flash device is a memory device or a proxy or a substitute for one, because it is not. It is a storage device. It does not provide byte level access, was never meant to. It's not as fast as the main memory. These devices provide page level access, where a page is not the same as a virtual memory page. Okay, again, don't confuse with that. The flash world, or in the flash world, a page is between 512 and 4096 bytes, which is basically what, half KB and 4 KB. A page, depending upon the vendor of the device, could be anywhere between half or 0.5 and 4, anywhere in the spectrum, a power of 2. What you normally do is that you don't send every write or every byte to flash. You accumulate the writes. You could accumulate the writes in some sort of a buffer in main memory, or some sort of a buffer on the chip, in the caches or whatever. And then most flashes do have DRAM backed DRAM backed cache, and then you sync it to the flash device. So pages are grouped into blocks, no doubt, right? And why is that done? Well, we will see in a second when we try to erase. But the fact is that it's kind of a dual level hierarchy, where you can read at the level of a page, where a page is defined like this, and pages are grouped into blocks for a different purpose, which is for the purpose of writing, and we will see in a second why. So blocks contain, so the way you remember is, a page is an atomic unit and a block is a block of pages, and a block would typically contain somewhere between 32 to 128 pages. We always read and write data at the level of pages. However, writing comes with an additional caveat, which I will discuss, because for writing you will have to erase and rewrite, because there is an asymmetry here. I will come to it. What happens is that page, once you have written, cannot be written once again, right? That is because of the high potentials and so on that you need to apply, that a page that you have written to cannot be written to once again. It has to be erased first, and erasing is very difficult. So that is why what you do is that erasing is kind of like a big potential affair, where a lot of current has to flow. So you would like to erase a full block in one go and then write to the pages. So even if you want to write to one page in a block, the entire block has to be erased, right? So that's how bad things are. That is why it's a good idea to cache writes. So you erase a block first and then write. So let me talk about the asymmetry. So the asymmetry is that you consider a fresh page, then programming is writing a 0, which we have seen how to do it. By default it contains 1, so don't do anything. You cannot convert from a 0 to 1, unfortunately. That's the unfortunate part, without erasing, and you erase a full block of pages at once. You cannot erase a page in one go, and that is the sad part. Erasing means set everything to 1 and now then go and set ones to zeros. But again, conversion of 0 to 1 is what cannot be done at a page level. It has to be done at a block level, where you erase the entire thing. Right, so that's again, that's to say that is by far the biggest problem with not only flash but all other NVM based devices, that writing is tough, reading is easy. They are optimized for fast reads, writing is tough. So when you write, but that's not the only problem. We will see that this is the start of our problems, and problems are many. How do you write to a page after writing to it once? Well, what you do, again, bad idea, but what can we do? Copy the full block to a fresh block somewhere else on the device, which is not programmed, other than the page that you intend to modify. In the fresh block there, what you do is you replace the contents of that page that you didn't modify with the contents of the modified page, which basically means that you go to that page, look at every bit. If it is 1, then let it be, right? If you wanted it to be 1, let it be, or if you want to convert a 1 to a 0, then you program, right? So the idea basically is that, look, if you consider, if you are like moving a full house with a lot of furniture, you are not allowed to kind of change one sofa in a house, right? The main thing is, as illogical as it may sound, it is like move all the furniture from one house to the other. But then if you are not interested in a sofa, then don't take it and buy a new sofa, right? That's unfortunately the way it is. That is why DRAM caching becomes very important, very, very important, to precisely reduce such occurrences, because these are very power hungry and slow operations. But as I told you, this is just one of the problems. There are a few more of a far worse nature. Unfortunately, as it turns out, a flash device can endure a finite number of program erase cycles, because it's a program erase cycle, right? You program first, next time you will have to erase because you cannot reprogram, then you'll program. It's a P cycle, program erase cycle. A lot of the flash devices, specifically multi-level flash devices, can only survive for 50 to 150,000 PE cycles, which means that you can't use one of our pen drives, right, the ones that we have in our pockets, to run an OS or to do anything else, because it has a finite shelf life. It is not meant to be used that frequently, because after few years of usage it is going to die. Why will it die? Because it has limited endurance, which means if you have a pen drive in your pocket, use it rarely, use it sparingly, but don't ever think of using it as a frequently used storage device like the hard disk. It was never meant for that. So how do you kind of make a bad situation slightly less bad? You maintain a program erase counter for each block. You assume that addresses on flash, you virtualize the addresses, you assume that the flash addresses are virtual addresses which are mapped to physical flash addresses. They are not virtual and physical in our regular TLB page table sense, but you get the idea. What you send is a logical address which is mapped. Maintain a mapping table which is mapped or kept inside the flash device itself. You decouple the actual flash address from the logical address because you have a mapping table anyway. Mapping means decoupling. And furthermore, you are allowing the hardware to remap and remap obliviously. Remap oblivious of the fact. Who is oblivious? The kernel is oblivious, the user is oblivious, everybody else, that inside the flash device something of this nature is happening. So what is happening? Mapping is happening. How do we ensure that mapping is optimal? Bear with me for one slide. So what we do is that, so here I have a simple diagram. Kindly look at 1, 2, 3 and 4. 1 is step 1, 2 is step 2. So when I see that a certain physical block, right, has a very high PE count. PE count is program erase count. I would like to map it to some other logical block which has a low PE count, which is infrequently used, and move this to some other place, some other physical place which has not been used a lot. So what I can do is I copy the contents of this frequently accessed block to a free block, right, so which is kind of used as a scratch pad, right, temporary area. I do that. And then what I do is I erase this, and then I take a block that has seen a very low usage, and then I transfer the contents over here. Finally, what I do is I free up the free block, which was anyway a temporary kind of a scratch pad area, right, just to, because we are doing a swap, right. So for swapping you would always need a temporary variable unless you are allowed a XOR or something, and that option is not available to us in any case in a flash drive because of the physics. So once this is free, you transfer this over here. So what happens is that you are trying to do what is called wear leveling, that you are ensuring that all the blocks in the flash device kind of, their wear and tear happens at the same rate. So let me give you a practical example. Let's say you have a car. It so happens that the left tire, which is under the bonnet, is basically, its wear and tear rate is high. That's typically the case in India because people throw a bunch of things on the road when they are walking, and then the tire kind of goes on top of them, and then some of these end up being nails, and then you know what happens. So that is why if you see most of the time these punctures, right, happen to your left tires, particularly the tires that are on the front side of the car. So a good idea, or let's say a lot of garage people will tell you that you should actually rotate the tires. Once a tire has seen a certain number of puncture repairs, because the tire also has a limited endurance, right? Consider it a puncture operate cycle, like a PE cycle. So a tire has a limited endurance, and after 5 or 10 puncture repairs, the tire repairman will tell you, look, your tire can't be repaired any further. it's much better you buy a new tire, which is quite expensive. If you want to be kind of smart, your right side of the car does not see that many punctures, right? This is, anyways, this is something purely in the Indian context, so people abroad may not be able to fully appreciate it. But the fact is that what we normally do in India is that on a regular basis in a car we rotate the tires, in the sense that if, let's say, my left side bonnet side is kind of seeing a lot of wear and tear, then I will transfer it to my right side trunk side, right? So that way. So you get the idea. The idea is if I rotate them, all my tires will age at the same rate, which is anyway what I want. So this same remapping idea is or does happen in flash devices as well. Another problem, as I said, our problems never end with flash. There is something called read disturbance. If I read a given cell continuously, the neighboring cells in a NAND flash, as you can see in NAND flash, you have these devices all connected in series, right? If I'm just reading these are the neighboring cells. What happens is that they gradually start getting programmed. Programmed means they start getting some charge in their floating gates. So what happens is that the rest of the cells have to be enabled. The voltage at their gates is greater than Vt plus typically, but it's not as high to pull electrons. But the point is, you are enabling them with a threshold voltage which is more than Vt plus for a protracted duration. That is enough to kind of suck electrons, and they can gradually tunnel and go up, not at the rate of programming, but still, after all, dewdrops can fill an ocean. So what happens is that after a lot of usage, these cells get programmed, and the moment these cells get programmed, this is read disturbance. In the sense, you are not accessing these cells, but they got programmed because you enabled them, and you will start accumulating faults. So you better have a good error correcting code to fix it. Again, can be fixed with a little bit of computer architecture, not software involvement but logic involvement. You maintain a read counter for each block, and the moment it exceeds a certain threshold, you copy the block to a new location, right? And then you start from a fresh state. So again, you move these blocks around. So then in a new location, the moment you are doing the programming and so on, you'll start from a fresh ab initio state, and whatever is the temporary amount of charge that you have accumulated, that will cease to be an issue. So again, a lot of this is done inside the flash controller, but it also comes down to the level of the device driver also, that if you are dealing with a flash device, shelf life is a big issue, because you have many of these hard drives which are a bunch of flash devices. So you have to do wear leveling at the level of the device as well, not just intra device but also inter device, and that is where software actually plays a big role. And flash device driver development is interesting, and is there are conferences dedicated to it. It's that important. Next we come to the hard disk. The hard disk is our tried and tested workhorse that we have been using for the last 40 years, very reliably so. Before I discuss what is a hard disk, I need to tell you a little bit about Nrzi encoding. Without that, we will not understand it fully. Nrzi is non-return to zero, don't return to zero, inverted. What does it mean? So we will have a clock, and let us say the clock is, what's a clock? So basically the data sequence that I want to send is, let's say, 0111, 0101, 000. The data that I am sending, kindly, this is where I need your indulgence and your attention. If I am sending a 0, I just maintain the same voltage, I do nothing, right? 0 maintains the same voltage, nothing is done. If I am sending a 1, that is when I flip the voltage. So this is, let's say, the 0 volt level. So from positive delta, I go to negative delta. Again a 1, again I flip. Again a 1, again I flip. 1 means flip, 0 means no flip. Then 0, I continue. 1 means flip, 0 means no flip. So a USB channel, which is by far the most popular physical channel because all our devices run on it, uses the Nrzi encoding. Okay, so this is how data is transferred on any USB link, right? I mean, it does more. I mean, you will find that in my undergraduate computer architecture book, but this is the base. So what happens is that, what is the advantage of doing this? The advantage is that this is synchronized with the clock. It is easier to retrieve the signal because you can kind of align yourself with these transition boundaries. Of course, what can be a showstopper or a party breaker is that you could have a bunch of zeros, which means that you'll have a same static signal. Now let's say I have 100 zeros. What stops the receiver from reading 99 zeros or 101 zeros? Well, this is where you introduce dummy bits, which means that if you have a run of zeros, you force a 1. So that's a dummy bit. It's reducing the bandwidth of the channel, but by a little bit. But trust me, this is something that you need, that you introduce a dummy transition where it is known. So this is something that will get filtered out later. A dummy 1 is introduced such that there is at least one transition, such that the receiver clock can synchronize itself to this dummy transition. Hard disks use the same idea, not with signals but with magnets. So it is magnetic storage. It is a sequence of tiny magnets. The direction of magnetization determines the value, of course, of the magnet, but again they use Nrzi. So it is not the direction of the magnetization, but it is just the fact that is the direction remaining the same or is it changing? The same as voltage, the same as magnets. In this case, the direction remaining the same, I go 0, same logic. In this case, the direction, let's say direction is from south to north. There is a flip, so I make it 1. Again, in this case, it is the same, I keep it 0. Again, in this case, you can see a flip, it becomes 1. So the key point is that in this case also Nrzi is happening. In this case also dummy bits are needed such that when you are reading the hard disk, you can maintain a sense of synchrony or a synchronization. So again, you keep it as magnets. A good thing with hard disks is that everything is stored magnetically. So there is power is removed, the data is still stored. Again, never ever bring a strong magnet in front of a hard disk because its data will go. How does hard disk store data? Well, this part is simple. You store these magnets, this sequence of magnets in concentric rings. Starting from the center actually has a hole. So in the hole, the spindle kind of fits. We'll see a 3D diagram. Each of these circles or these concentric rings, they are called a sector. Okay, sorry, they are called a track. I stand corrected. Each of these concentric rings is called a track, and then within this, a sector. All sectors incidentally are the same size. This is called a sector, and a sector typically contains a block of data. I won't blame you if you tell me that this word block is being used again and again and again in the same same word, many different contexts, but again, my apologies for that. But the fact is that a sector contains a block of data along with its error correction code. It is typically 512 bytes for most of the hard disks. I mean, consider this a standard. It's kind of half KB. Consider this to be a standard, that it is 512 bytes, and that is the size of a sector, and a sector contains a block. And of course, you would have tracks. The tracks closer to the center, they will have fewer sectors. Tracks towards the outer part of the recording surface will have more sectors, right? So this entire recording, a single recording surface is called a platter. Okay, this entire circle is called a platter, which is divided into tracks, and a track is divided into a sector, and the data is not it's not uniformly stored, right? So you will have more sectors in tracks which are outside, towards the outside. The structure of a hard disk is like this, very interesting. Kindly pay more attention than what you are doing. So what you have is the internal of a hard disk. As you can see, you have multiple recording surfaces here, multiple platters. Both the sides of this disk are typically used, right? Both sides, both the recording surfaces. Then you have a spindle that is connected to a stepper motor which rotates at a fixed angular velocity. You have this head over here. The main job of this head is to monitor changes in the magnetic field, and we all know from our high school days that any change in the magnetic field induces a current, right? And this current is something that can be measured. And as I also said, the current will indicate a logical 1, the absence of current will indicate a logical 0, and to maintain synchrony, dummy bits, etc. are all required, which are there. But the key point is that this rotates. You have multiple recording surfaces, but at one time you are only reading one surface, not multiple though. And this recording head over here is anchored here, and this rotates here like the rotation is angular. And so first thing that you do is you position the head on the right track, and then of course if you consider all the tracks of all the recording surfaces, it's called a cylinder, because as you can see it looks like a cylinder, right? If I do this and kind of pull it on the z axis, it will look like a cylinder. So you choose the right cylinder, some minor adjustments have to be made. Once the head is on the right track, you wait for the sector to come below the head, because every sector would have a sector ID, so you wait for it to come below you, under you, and then you read the sector and you transfer all the data. If it's a read, you transfer it out. If it's a write, you transfer it in. So writing would require what? It would require the reverse, where essentially you would apply a magnetic field and change the magnetization directions of the magnets. In the case of reading, you would see whether the change in the direction of magnetization is inducing a current or not, which of course with sophisticated signal processors you can detect. So what I said, this is a diagram that shows the same thing, where I have a spindle motor, electronics for that, and the actuator is what moves these heads. And these heads, well, you have a head and you have an arm, the arm moves the head, but the idea is that only one recording surface is read or written at a time. It rotates, since it rotates on an anchor point, the rotation is angular, right? It's a rotation and it's angular. And the read write head, as I said, waits till it comes under the right track, then it waits for the right sector to come under it, then you read or write, and that takes its fair share of time. And of course you have this bus interface and so on, and the bus interface means it is going to the South Bridge chip, and of course the bus will have its own signaling and so on. So let's not worry about that right now. So the math of a hard disk is simple, very simple. Position the head on the correct track. How much does that take? It takes seek time units. Wait for the desired sector to come under you. How much time does it take? Is the rotational latency. On an average, how much is that? Well, so let's say it takes r time units for a full rotation. On an average, it's r by 2, right? On an average. Reading or writing data, which would also entail performing error correction, checking, correction, framing, all of that, right? Packaging and transferring all of it, because we are looking at 512 bytes in one go. That's typically the read write transfer size, and you transfer it to the CPU. The total disk access time, again need your attention, is T seek time plus rotational latency plus transfer time. That was simple given all my description. Here again, like flash, we have a logical address and a physical block address that again is needed, along with the usual paraphernalia of a DRAM cache and a mapping table. The hard disk, needless to say, would internally convert the logical address to a physical address. Physical address in this case would mean which recording surface, which track, which sector. You will also have a recording surface which is dedicated for storing mapping information, and needless to say, all storage devices typically have a DRAM cache to absorb writes and reduce the underlying bandwidth. The hard disk can also use this mechanism to mark bad sectors, which means sectors that have developed faults. How do you know something has developed a fault? Well, its ECC is not able to correct. Then you don't use those sectors, and whatever was being mapped there is sent to a good sector, right? That also this bad sector removal, and all of this can be done in the mapping table. All you have to do is you have to remap. A file in general, what is a file? It's basically a contiguous set of bytes that we are assigning a meaning like a video file, audio file, voice file, which is stored on the disk. You ideally don't want to be split, right? You don't want a file to be split, right? You don't want it to be split and be all over the disk. What you want is that you want the file kind of to be contiguous on the disk, such that it needs to be contiguous in the track, such that once I start reading it, I no more seek time and rotational latency business. I just read this sector, the next sector, and so on, and then I just go to the next track. Again, I read the sectors. You kind of want to be stored as a spiral, right? Every file you would like to get, you want it to be stored like this, and then the next one, sort of like a spiral. Okay, if you get the idea. And that is where there is a need to defragment the disk. All operating systems, Windows, Linux, everybody, they have a defragmenter. This is precisely what it does. It ensures contiguity on the hard disk. Once your system becomes slow, most people advise, and they correctly advise, that you defragment the hard disk. Its performance will improve, which it often does, and all the bad sectors will be identified and moved to some corner. You'll not map to them again. Of course, for flash drives and so on, because a lot of modern machines come with flash drives and NVMs and so on, they don't require this. They require, for them, this contiguity is not important the way it is for a hard disk, because it's a mechanical device. And also the other thing is that a laptop with a hard disk, if it falls down, you actually care about the hard disk. It's a mechanical part, and this mechanical part is so sensitive that the recording surface is maybe 1 or 2 nanometers above the or below the head, right? Kind of a small cushion of air keeps it above. It's very sensitive. So once you drop a laptop with a hard disk and the hard disk goes, you are literally gone. The hard disk is gone. So given that hard disks have a high failure rate, why? Because number one, they are temperature sensitive. The moment you have a lot of hard disks, you definitely need an air conditioner that is running at 18 degrees Celsius to maintain the health of the storage system. Because hard disks, as you can see, have a lot of mechanical components. They are highly temperature sensitive. Because again, why? Because temperature has this expansion, cooling and cooling things. So the moment small inaccuracy, given the massive amount of data that we store, your entire hard disk can go. It's mainly these mechanical and temperature issues that kill our disks. So that is why what you should do is that whenever you are buying an expensive server with multiple hard disks, you should always go for a RAID based solution. What is RAID? RAID is redundant array of inexpensive disks. Inexpensive disks because hard disks are cheap. And redundant array means you keep some additional hard disk just for the purpose of improving reliability. Okay. So basically, it turns out that RAID can improve reliability as well as increase bandwidth. What about bandwidth? The idea is that you can read different blocks from different disks in parallel. Well, that's a great idea. But our main aim is reliability. If performance increases, we don't mind. But again, that's not our primary incentive. So let's look at, so there are at least 7 kinds of RAIDs that I know of, including a few more which are combinations of them. Let's look at this. RAID 0 means you distribute data across disks. If I have 2 disks, disk 1 and disk 2, I put block 1 here, block 2 here, 3 here, 4 here, so on and so forth. And a block is this half KB thing, right, which is stored on a sector. This is known as data striping. B1 here, B2 there. This has no reliability. Of course, your bandwidth can increase if, let's say, you are accessing an even number and an odd numbered block in parallel. Both the hard disk can give you data. That's good idea, fantastic idea. But the bandwidth can increase. It will not increase if both the blocks are on the same disk, incidentally, but otherwise it can increase. So we can read even and odd blocks in parallel. Our bandwidth will increase, but reliability we are not getting. So RAID 0 is okay for performance, but that's a very bad idea for reliability. Let's go to RAID 1. RAID 1, the idea is you keep 2 copies of these blocks. Keep B1 here, 2 copies. If one hard disk dies, at least the other hard disk is there, it can supply. RAID 1 can also improve performance because you can read B1 from here, B3 from here in parallel. What's the issue? You can read and write in parallel. So RAID 1 also improves performance in that way, that it kind of doubles your read write bandwidth, right, as opposed to striping, which was kind of probabilistic. This is doubling. Of course, the usable capacity is reducing by 50%, or on the other hand, if you want to kind of reason on the other side, you can say it is increasing by 100%. But the fact is that I am having two hard disks, one is a mirror copy of the other. So your usable capacity is reducing by half, is becoming half. Then you have RAID 2, 3 and 4, they are all kind of different flavors of the same thing. So what you do is that you store, let's say B1 here, and I am deliberately saying B1, I am not saying it's a block, because I want to keep that flexibility. B2 here, B3 here, B4 here, P1 is nothing but the parity, okay. And so basically over here, this is nothing but the parity. So what I do is that if you see P1 here, what is the parity? The parity is basically the XOR of these. So if I just go back and show it here, it is just the XOR. XOR means B1 XORed with B2, XORed with B3, okay. So this is the parity, is the standard XOR arithmetic, and similarly P2 is the XOR of this. So this will also do the same thing. Its storage overhead is not that high. In fact, in this case, the storage overhead is what? It is basically 20% in this case. 20% is what you are wasting, as opposed to, in this previous case, if I just go back, you were wasting half of your storage was getting wasted, but in this case that's not happening, right? Thank God it's not happening. So it's clearly immune to one disk failure, because why? If let's say this disk dies, then there is no problem at all, because then you can reconstruct the data from the data of these disks and the parity, right? Even if the parity disk dies, you can always add another disk and recompute the parity. So this is immune to one disk failure. Furthermore, it is improving bandwidth, but then of course I didn't say what RAID 2, 3 and 4 are for, but the idea is that RAID 2, 3 and 4, RAID 2 and 3 are not used, and you will see why not, but you can always find a specialized situation in which they will be used. So RAID 2 stores 1 bit, okay, so which means that this B1 is 1 bit, B2 is 1 bit, so this is bitwise. It's a good idea if you want to parallelize the process of reading a single block, because this is intra-block parallelism, which basically means that if you want to read 512 bytes, you can parallelly read parts of it. Nobody does that. It's a very bad and impractical idea. Don't even think about doing it. Similarly, in RAID 3, this B1, B2 and so on represent 1 byte. That also is an impractical idea. Don't even think of doing it. Of course, this increases intra-block parallelism. But in any case, in a storage device, people care about inter-block parallelism, not intra-block parallelism. Finally, RAID 4 is something which we like, which is basically that you want to store data. B1, B2, B3 are all blocks. Inter-block parallelism is there, which basically means that I want to read this block. Well, no problem, go ahead with it and you'll get the full block. Reading is not an issue, because here we are not assuming any corruption, we are not assuming any data corruption, okay. That's the important part. We are just saying it's like a fail stop failure model. The entire hard disk just stops working and it just dies, the entire hard disk just dies. We are not assuming that we are running and something happens and the data you may not trust. That doesn't happen. You have enough ECC to verify that. So this is predominantly a mechanical failure which we are looking at, which is anyway 99% of real world cases have that. You have sufficient ECC. The idea is that reading is fast. In this case also, reading is the bandwidth is improving. You want to read this and this in parallel, no problem, go ahead. Is just reading 2 or writing to 2 on the same, well, let me not talk about writing yet, but reading to 2 blocks on the same disk is slow, right, because that has to happen in sequence. Now let's look at writing. Writing is not as simple as what you think it is. So let me first clear up the screen, and then, because writing is definitely not something that which you and I would like. So let us say we replace B3 with this. So let's say this becomes B3 dash. There is no reason to read the rest of the blocks and basically recompute the parity, right? That is not required. Just in case you are thinking that is required, that's not required. What you have to do is the new parity, let's call it P1 new, is basically old P1 XORed with the old value of B3, XORed with the new value of B3. Okay, that's all that you need to do. You need to, proving this is a homework for you, that this is all that you need to do, which is read the value of P1 and XOR it with B3, which essentially takes away B3's contribution, and XOR it with B3 new. Alright. So this is all that you need to do. You don't have to access the rest of the disks, just in case you thought there is a need to do that. But that said and done, if one disk is dedicated for parity, all the writes will come here. This will become unreliable because of its high usage, and it will become a single point of contention, right? The latter is more important. It will become a point of contention, which you don't want. Any point of contention means heavy usage, which means lack of long-term reliability. So the single point of contention stuff we don't like at all, and this is not something that we would like to do or like to have. That is why what you do is RAID 5, which is the most common in any storage server, is distributed parity, where the parity blocks are distributed all across. So then all disks kind of age and their wear and tear, similar to flash, happens at the same rate. So that's the idea. You still have high bandwidth, no issues with it. You still have high reliability, and everybody is aging at the same rate. If you want more reliability, go for RAID 6. Look at this. So if you see the PowerPoint over here, you will see that we have, of course, we have more space wastage, and for every group of blocks, we have 2 parity blocks. These parity blocks are distributed all over the disks. So that is why, again, you don't have a single point of contention. Again, you have high bandwidth. However, we have additional reliability that out of these 6 disks, I can tolerate 2 disk failures, whereas in the earlier case, I was able to tolerate only 1 disk failure. Earlier case was RAID 5. If I go back to RAID 5, I can tolerate only 1 disk failure here, right? Because the overhead is 20%. In this case, the overhead is 33%. I can tolerate 2 disk failures. If you want bulletproof extra reliability, you go for RAID 6, where you buy 6 disks, 2 of them you keep them for parity. Well, not for parity, the parity is being distributed, but let's say you have a 6 disk system, where you'll assume that you will only be able to store data, which is 4 disks worth of data. But as I said, the moment you have RAID, your system becomes quite reliable, because the moment you have this red indicator on the hard disk saying that, look, hard disk is about to die, you just replace it, right? So that's not an issue, and no one is that unlucky that multiple hard disks will fail at the same time. So fine, we have discussed flash now, we have discussed main memory now. We will spend 3 more slides on NVMs, and then our lecture will complete, but kindly bear with me until we have discussed these 3 slides. So basically, as I said, 3 slides with NVM, we will then not discuss storage that much. We will move to the software aspects of the OS. See, the main problem with DRAM memory was that when the power is turned off, the DRAM memory loses its data, which was not something that we liked. So we went for flash, and we said that fine, we will use flash. But then the issue with flash and other solid state technologies is that they have a limited shelf life, right? And writing is a big issue. Writing is a very, very big issue, because you write to a block, the block is transferred somewhere else, and then from somewhere else it is transferred here. That's a big issue. Non-volatile memory, which is essentially nothing but a storage device, is slower than DRAM memory, right? That you would expect, because DRAM is a single capacitor, but is faster than hard drives, so it can act like a regular storage. In fact, the laptop that I'm just using to present does not have a hard disk, right? It has a non-volatile storage mechanism. The generic approach is like this for creating any kind of device, be it flash, be it anything else. Construct a device or construct, some, I'm calling a transistor is also a device. So it needs to have two different physical states, right? Whatever the physical states be, it needs to have two different physical states which can be read or written. Designate one state a logical 1 and the other a logical 0. Fine. Create an array of such devices, have a method of managing the array, have a method of wear leveling, have a method of ensuring reliability, and reliability comes here with a big capital R. The reason being that reliability is one of the big issues, the limited shelf life, that bedevils and imperils the usage of such devices. What happens, which is good for us, that these two physical states, one would correspond to a high resistance state, one to a low resistance state, which is what we saw in flash also. If we set the threshold voltage between Vt and Vt plus, one conducts, one doesn't. So one is high resistance, one is low resistance. A quick one slide summary of NVMs. I will not go more than this. Flash, we have seen you have a floating gate. The floating gate traps electrons and then that changes the threshold voltage. If we set our threshold voltage between Vt and Vt plus, then the cell is said to be enabled and then we can find what is stored. We have ferroelectric RAM, which is much more reliable than flash. And the interesting thing is, like DRAMs, read is destructive, which means that once you read, you have to write, but still read writes are very fast. You don't have this block based thing that you have in flash. It is the fact that you use a ferroelectric material where its polarization, right, is a function of the voltage that is applied, that has been applied to it in the past. So what you do is you apply some voltage, it has a hysteresis curve. If you still recall from your high school days, a hysteresis curve looks something like this. And the hysteresis curve indicates what is its state of polarization, and different states of polarization have different resistances. You have an HRS, high resistance state, and a low resistance state, or something that can be electrically detected. Because how do you electrically detect? You pass you'll have a voltage, you'll pass a current and see, what's the current, right? So pretty much the idea is that the resistance has to change with the physical state, and the physical state can be a logical 0 or 1. So ferroelectric was ferroelectric, but it is quite reliable, very good shelf life. It is used a lot in the black box recorders and so on. MRAM is used a lot. In fact, this is going to be the most popular NVM device, where you take a ferromagnetic material and the direction of its magnetization, which is also a function of the current that flowed through it in the past. It's kind of similar to the memristor idea, that the past current that flowed through it will determine what is the current resistance of the cell. So basically the magnetization, there are two states, parallel state where one layer has a pinned magnetization, the other's magnetization can be changed, right? And MRAM also, the spin torque transfer MRAM is the most popular today. Let me write it, STT MRAM. And there the idea is you look at the magnetization, right? So parallel, anti-parallel. So this is very popular. Phase change memory is also quite popular. In this case, you rely on the state of the material, amorphous, one kind of resistance, crystalline, one more kind of resistance. You have a small heater that can convert from amorphous to crystalline, crystalline back to amorphous. A fast heating rate will make it amorphous, a slower rate will make it crystalline. ReRAM, again based on the history of the voltage applied, what will happen is between the anode and the cathode, which are the two ends of the cell, a filament will form, and the filament essentially determines the resistance. The existence of the filament is low resistance, the filament not existing is high resistance. So of course, as you can see, there is a lot of physics here. There are a bunch of these devices which are all non-volatile, maintain their state when the power is turned off. They have different redundancy requirements, they have different methods of operation. Most of them come with their own hardware, so they kind of take care of themselves. But as I said, when you are considering large flash storage or heterogeneous storage, little bit of flash, little bit of NVM, little bit of hard disk, it is important for operating systems to optimize their operation in terms of performance, in terms of short-term reliability, in terms of long-term reliability. So I think I've spoken enough. So this is where this lecture ends. We'll now look at device drivers and OS code.